Okay, let's go over this. So we're given our recurrence, and our goal is to solve the recurrence. We use backward substitution to do that, and then we'll try to plug in a value for I once we've identified a pattern to get our initial condition to be satisfied. Okay, so we'll do our recurrence. We have f of n equals f of n minus 1 plus 3. So what we can glean from this is each time we make a recursive call, the input value shrinks by 1, and we perform 3 basic operations. Okay. So we're going to substitute in for this. We're going to get f of n minus 2, because that would be the next recursive call. And then we're going to add on 3, because each time we perform a recursive call, we run 3 basic operations. So if we are figuring out how many basic operations we perform at n minus 2, that has to be the same number of basic operations as n minus 1, and then we have to add on 3 to compensate. Okay? Now, this original plus 3 that existed up here, this comes down as well. Okay, so we get plus 3. So we'll simplify this. We'll simplify this to be f of n minus 2 plus 6. All right, let's do it again. We'll substitute for this f of n minus 3 plus 3, and then we'll bring down this plus 6. F of n minus 3 plus 9. Okay. Do we have a pattern here? We have n minus 1 plus 3. We have n minus 2 plus 6. We have n minus 3 plus 9. What can we simplify this to? Good. Easy enough? So now that we haven't solved it yet. Now that we have identified a pattern using backward substitution, our goal is to get rid of this f of n. Okay? The way we get rid of this is by looking at the initial condition, which is f of 3, and we're trying to get what is inside of here to equal 3. So, what can we substitute for I? Let me write this up here. F of n minus I plus 3. So we're going to plug in some value for I, and we're trying to get a 3 here. That's what we want to get. We want to get a 3 here. So what can we subtract from n?
N minus 3.
Good. So we're going to say f of n minus, and we're going to plug in there n minus 3. So n minus 3 is being substituted in for I, plus 3 times n minus 3. Okay. So now we can simplify this. This is going to give us f of 3, because n minus n minus 3 gives us 3, plus 3 times n minus 3. What's that give us? 3n minus 9. So, we still need to get rid of this, but luckily we know that this has a value of 2. So we'll simply say 2 plus 3n minus 9. Can we simplify that further? What is it?
3n minus 7.
So now we have our recurrence solved, because we got rid of the f of n on this side, and we have our algorithm expressed in functional notation. So now we need to pick out the dominant term. We have two constants here. We have the 3 and we have the -7. Both of those we ignore, because we don't care about them. Right? And so that leaves us with n. So our dominant term is n. And that becomes our class as well. Yes?
So in the last example, when we noticed the pattern, we got a, or it was a instead of f, but it was a n minus I plus I, even though it was going up by 2 in each constant. So why isn't, how come this one is different when we do 3i, while the other one we could have just went straight up I?
Good question. The reason for that is the value inside of the parentheses and the value outside of the parentheses were increasing by the same amount. Okay? So if you put 2i here and 2i here, because I is literally any number, it's the same thing.
It's like terms. So.
Right. It's not wrong if you did that.
Okay.
If you put 2i here and 2i here in the previous one, that's not wrong.
Okay.
Okay. Good question.
Follow up on that. Would you say, for the purposes of accuracy, like you want us, like if this is the case, then it doesn't matter if we do the constants or whatever. We just have to get ON. It's just for accuracy and understanding it.
It's like in calculus when you're doing limits, and you know it's eventually going to get there, but it doesn't. You know it's approaching 0 or whatever, but it doesn't actually get there. Even though in your head you know what that means, it's the same thing here. Like in your head you know what it means, but you have to show. Other thoughts, questions on this? Yes?
Is it always going to be ON?
No, it's not always going to be ON. Probably for this class it'll probably be ON because this is an introduction to algorithm analysis. And to be totally honest, I'm interested in you understanding the process. The only difference between this and one that is n squared or one that is log n or something else is algebra. That's it. It's just math. And so you've taken enough math courses. I think when you get if you're a computer science major, the way the requirements are now, if you do if you do your related works in math, you actually end up with more math credits than you need for a minor. So it's a lot. So you take a lot of math courses. So for that reason, I focus more on the process as it relates to computer science rather than the algebra necessary to do log or n squared or other ones. So, good question. Other thoughts on this? Are we ready to move on? All right, so before we close the book on this, you will see this again on your final. This is a very accurate representation of what I expect you to know. Yeah, I might give you one of these on your final. I give you an initial condition and a recurrence, and I say solve it. Right? So what we just did here is the extent of what you need to know. And you can expect this level of difficulty. Okay, yes?
So is solving the recurrence used for anything besides finding the simplicity of it?
What do you mean?
Or, I mean, sorry, the big O notation.
Oh, the complexity?
I totally went backwards.
No, that's okay. Like, does this have application outside of this?
Yeah.
Not to my knowledge. Somebody who knows more about algorithm analysis or life might be able to give you another application for this. I haven't. I can thoroughly and confidently state that I have never needed this for what I've done in game development. Okay, now, caveat. Neither have I used calculus or this or this. And I could go through and I could name a half dozen quote-unquote difficult courses that I've taken that I haven't directly used. Okay? That's not to say those were worthless. Okay? It's not to say you learning this is worthless. I think you guys know my teaching philosophy at this point well enough to know that I'm not going to teach you something that I think is stupid or make you learn something to pass a test just for the sake of passing the test. Okay? This stuff, and I'll be honest with you, if there are 50 of you in here, 49 of you will never look at this again in your life. Totally honest. Same thing with calculus and difficult math courses. Most of you will never directly use that math. Some of you might go into a specific field where you use that. And contrary to what you might think, the people that design the curriculum and the people responsible for setting up the required courses for your degree, they know this too. Okay. So that begs the question, well, why do we take the courses then? It's because learning this stuff, learning calculus, learning math, teaches you more than direct application of what you're learning. Okay? What I mean by that is, you are learning a lot more than you think you are just by learning this. Okay? It's like working out for your brain. It allows you to analyze things better. It gives your brain a larger capacity for solving problems. Okay? It trains it to do certain things. Okay. Does it make sense? You guys understand what I'm saying? All right, so trying to give you a little bit different perspective when you learn stuff that you think is worthless or never going to learn again. You're doing things to your brain, good things, that may not be initially obvious. Or, yeah, interesting. Does that make sense? We good? Can we move on? I don't know how we got on that. So that's one of the things I wanted to do today. The other thing is actually way up here. We skipped it. We typically cover it the first day, but I think it's better to learn it last. So I'm changing things up and we'll see how it goes. So we have talked a lot about recursion. Talked a lot about recursion over the past 2 class periods. Okay, recursive thinking, recursive analysis. And the reason for all of this is because we're getting ready to get into a data structure that requires recursion in order to use it. Okay? So I mentioned before that the next data structure, which will be in next class, is on binary search trees. Okay, so we're going to get into binary search trees. And in order to traverse, which means go from one node to another, kind of like you would do a linear search through an array, in order to go through a binary search tree, you have to do it recursively. Okay. We're going to do that by learning tree traversals. Right? And there's 3 different types that we're going to look at. All of them are the same thing, but the order in which you go about them are different. Okay. So I'm going to pause here and switch this battery. Okay, so let's resume. All right, so we're going to do tree traversals. All right, so here's how this works. Here's a sample binary tree. Okay, and the way it's set up is each one of these squares is a node. It's an object in the tree. And it has a reference. There's a reference here, and it has a reference here. This one doesn't have a left child. Okay, and we've talked about binary trees before, so this shouldn't be terribly different. But we're not interested in how the structure works at this point. What we're interested in is how we go about traversing it. Okay? I want to define what a traversal is first. Okay? If I said, here's an array, search the array and tell me if this number's in the array, that would be relatively easy. Okay? But when we traverse something, it's a little bit different. All right? To search something means you go through the data structure with the intent of finding a specific item. Okay? If you find that item, you stop. A traversal is different. With a traversal, you visit every node in the structure and you aren't necessarily looking for something specific. You just want to visit every node. Does that make sense? This would be the equivalent of loop through an array and print out everything, as opposed to loop through an array searching for XYZ. Does this make sense? Yes? You can traverse any data structure. Okay? It's a process of visiting all of the nodes. Any questions on the difference between searching and traversing? Okay. So what we're going to look at are 3 different traversals. All 3 traversals will visit every node. So it doesn't matter what traversal method you use. All 3 of them will visit every node. The difference between the 3 traversal methods is the order that the nodes are visited. Okay? One is not better than the other. They're just different. Okay? It's like, should we loop through the array starting at element 0 and going 0, 1, 2, 3, 4 all the way to the end? Or should we loop starting at the last one and go -1, -2, -3? Okay? Both would do the same thing. But there are some situations where it's better to start at the beginning and go. There are some situations it's better to start at the end. Okay? Does that make sense? Everybody good? All right. So let's look at this first one. This is known as pre-order traversal. Pre-order traversal. And the rule for pre-order traversal is root left subtree right subtree. That's it. In that order. Root, left subtree, right subtree. What's a subtree?
Branch.
Good. So, when we use the word subtree, we're referring to a grouping of 3 nodes. Specifically, a root and its children. Now, it's possible that that root doesn't have children. Okay? So, for example, this is a subtree. And what can be difficult about dealing with subtrees and subroots and this sort of thing is that everything is very context sensitive. Which means, depending on the context that we've defined, how we identify a particular node is going to be different. So for example, in this case, we would say that 1 is the subroot. Right? Because in the context we have defined, which is the blue circle, node 1 is the root or the subroot of that grouping. Okay? We would say that 2 is the left child, and 3 is the right child. Easy enough? Now, if we change the context and then circle this, we would say that our subroot is now node 2, where node 4 is its left child and node 5 is the right child. Okay, easy enough? Makes sense? So, here's what I want you to take away. We're always looking at groupings of 3. When we're doing traversals, we're always looking at groupings of 3. We have a subroot, and then we have that subroot's 2 children. Okay? If we specify 3 as the subroot, there is no left child, but there is a right child. Okay? Any questions on this before we get started? All right, so what we are doing here is we are going to run pre-order traversal, and we know already that the purpose of a traversal is to visit every node in the data structure following root, left subtree, right subtree. So, you always start at the global root. The global root is the root of the entire tree, which is node 1. Right? You always start there, and so we will define our context as such. Good so far? All right. Now, what I want to do is, just for some notation purposes, I am going to write root, left subtree, right subtree. We'll abbreviate them like that. Because I want to check them off as we visit them. Okay? And what we're looking for here in terms of an answer, so if I gave this to you on your test and I said run pre-order traversal on this tree, what I would be asking you to do is telling me the order that the nodes would be visited. Okay? And so as we go through and we determine the order that they would be visited, I want to check these off so that we know we've done them. Okay? So, the first thing that we do is what? On the list, what's number one? Right, 1, 2, 3. First thing we do is the root. So, over here I'm going to say the order. The first one is node 1. We do that first. Alright, I'm going to check this off. Now, what's the next thing we do? Left subtree. Now, notice what this doesn't say. This doesn't say left child. Okay? It says left subtree. A subtree refers to a grouping of 3 nodes. Good. And so when we see this, this actually indicates a recursive call. So we're going to recursively call pre-order on the left child. So it works like this. Now we are here. Now what happened to our blue one? What are we doing up here? We're waiting, right? We're just waiting. We have to wait until we finish this. So we made a recursive call. This is the example of one of our tools breaking. We can't complete the blue one until this one finishes. And this is why we spent a good bit of time talking about recursive process. So again, when we make a recursive call, this creates an entirely new instance of the same process. So here, we're going to write root, left subtree, right subtree. And we start over. What's the first thing we do?
Check the root.
Check the root. Remember, we start over. We perform a recursive call, we start over. So, we check the root, which is 2. Okay, so that's next. What do we do next? Left subtree. Okay? So we do a left subtree call, which is here. Alright, we've got root, left subtree, right subtree. First thing we do is root. Got it. Put a 4 there. Next thing we do is a left subtree. Is there a left subtree? No. So we don't do anything. Is there a right subtree? No. It's null and null. So have we finished this particular call? Yes, we have. So we finish this, and we simply go back to where we were. Not up to the blue one, because we didn't call the black one from the blue one. We called the black one from the red one. So we go back to the red one, and now we've done the left subtree. Repeat the process for the right subtree. So we come here. Root, left subtree, right subtree. First thing we do is root. Got it. There is no left subtree. There is no right subtree. So we finish that. Return to the previous. Now we have done the right subtree. Because we have done all 3 of those, we can finish this. And we will return back up here. And now we've done the left subtree. All right, let's finish this off. Then we go to the right subtree. And so we go to the right subtree, and we're looking at this. So we have root, left subtree, right subtree. First thing we do is root. Take that off. That gives us the value of 3. Left subtree. Is there a left subtree? No. Is there a right subtree? Yes. Root, left subtree, right subtree. Do the root. Check this off. And we get 6. There is no left subtree. There is no right subtree. So we finish this. Turn back to where we called it. We finish the right subtree. All 3 of those are done. So we can return to where we were. All 3 of those are done. until we finish. Answer 124536. Easy enough? Let's have you guys do it. So that's pre-order traversal. There are two other types of traversals. There's in order. There's in order, and there's also post order. You don't need to know this, though. Okay, you just need to know pre-order. In order, I believe, is left subtree, root, right subtree. And post order is left subtree, right subtree, root, or something like that. You'll need to do them on your program, but for the purposes of your test and this, you don't need to do them. We'll talk about your third programming assignment next class. Yay.
Awesome.
All right, so here's what I want you to do. Let's have you run, let's do in order. Run in order, which is left subtree, root, right subtree. Take a few minutes and do that one. Tell me the order that they would be visited.
This order was root, left, right. That's why we did root first, then we went left, then we went right. So this one, if it's starting from left, start root, and then you start from left. And then we actually so two is the root. Yeah, two is the root. So like if you look at the whole thing, it's group of 3. 1 is going to be the root, right? And then 2 is going to be the left side. So 4. So it's the same left side root. Left side root. Left side root. Yeah, so you can do the 2. Then root. Then right. Yeah. How did you go back to 4? That was just a guess.
Yeah, exactly. Actors
Or it's just chilling.
words, X's.
4 is me in all situations. 2, 1, 5, 4, 3, 6.
Got it? You guys need a minute? Okay, take your time.
It's kind of hard to visualize the recursion until we look at something like this, and then it's just like, okay, now I can kind of see them.
That's good.
Like when we're just looking at the equations, I'm just like, what's going on?
Thinking about it. I don't know. My thought process, I feel like that's wrong. The way I'm thinking. Oh. That's true because you go to. I like yeah.
All right, let's go ahead and go through this. We'll wrap up. So we want to do in-order traversal. An in-order traversal is left subtree, root, right subtree. All right, so I'm going to go a little quick. Left subtree, root, right subtree. So the first thing we do there is go down to the left subtree, which is this. We have left subtree, root, right subtree. So the first thing we do is we go down to the left subtree. We have left subtree, root, right subtree. This process is going to continue until there is no left subtree, which is the case here. So there's no left subtrees, we can check that off. Then we do the root, which is 4. So we put 4. And then we do the right subtree. There is no right subtree. So we're done there. So we've done all 3 of those, so we can X out of this one and return to the previous one. At that point, we have now done the left subtree. Next, we do the root, which is 2. Then we do the right subtree. So make a recursive call here. We do left subtree, root, right subtree. There is no left subtree. The root is 5. And there is no right subtree. We finish this. Return to the previous one. And now we have done the right subtree. We've done all 3 of those. So we return to the previous one and mark that we have done the left subtree. Then we do the root, which is 1. Then we do the right subtree. Right subtree is here. Left subtree, root, right subtree. There is no left subtree. The root is 3. And we do the right subtree. Left subtree, root, right subtree. There is no left. The root is 6. There is no right. Finish this. Return up here. We have now done the right subtree. Finish that. Return up here. We have now done the right subtree. And finish. Final answer, 425136. And so we only need to do 3 orders. On your test, that's the only one to make you do. On your programming assignment, you'll need to do all 3. And it's really simple. Like, the coding for this is ridiculously short, which is true of all recursive stuff. The code structure for recursion is incredibly simple. It kind of confuses you because you think something is difficult conceptually as recursion should look equally difficult in code, but it's not. It's really short. Right? Right. Yeah. It's basically just a very simple statement and a base case. Keep going. What's the base case in here? When do we stop?
Count through 1 through 6.
There are no more trees below it.
Correct. There's actually 2 base cases, okay, because we're doing multiple things. The first base case is when there's not a left child. The other base case is when there's not a right child. Okay? Because if you stop, we went left child, and then we stopped. Okay? 1 had a left child of 2. 2 had a left child of 4. 4 didn't have a left child, so we went on to the next statement, which was the root. Okay? If there's like 50 left children, we would go left, 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 all the way down. Keep asking the next person to print the report until we get to the intern.
Is that for this in order or for all of them?
That's for all of them. All right, so any questions for me?
You said there's a reverse order. Is that just right side through left side?
So post
Or
order.
post order?
Yeah. I don't know what it is off the top of my head. I probably should. I think it's left, right, root. But it might be, I think it's left, right, root.
We'll go over it.
Yeah, we'll go over it.